All right, so now we're going to look at what happens when we have a parallel circuit. So we've talked about series, and now we're going to look at parallel. All right, and parallel is a confusing word because you would think, like in geometry class, that the lines are parallel, and oftentimes when you draw these circuits, you might draw it that way. But parallel doesn't necessarily mean that the lines are parallel. It simply means that there are multiple pathways between 2 points. If you have multiple ways to get from point A to point B, then you have a parallel circuit, or at least a parallel component of that circuit. All right? But your general parallel circuits are going to look something like this. You got, again, a supply voltage. We'll call that Vs, which is going to have some positive and negative terminals. You're going to come out of that supply voltage, and you're going to have a resistor that you go through to get back to where you want. But you're also going to have the option to continue on and go through a different pathway that gets you there. And you might even have a third pathway to get there as well. So you have three, I call them loops, to get back to the supply. There's three parallel pathways. Sometimes you might see this same circuit drawn a little bit different. You might have a supply and comes up in here, and then maybe it splits three ways. And I'll show you how we can draw circuits. This is an identical circuit to what I just drew. Those are two of the exact same circuits. And I think that's important to understand. They look visibly different, but they both represent a pathway back to the supply that has three unique pathways. And so they are parallel. So coming out of the supply, you have a total current. There's I total. That's dictated by how many of these resistors we have, right, and what their values are. So I'm going to call this R1. It has a voltage drop across it, and it also has a current across it. Here's R2, a voltage drop across R2, and a current across R2. And the last one is, we'll call this R3. It also has a voltage drop and a current associated with it. All right, and so let's first talk about how we find that equivalent resistance. If I'm entering that highway, all I know is there are toll booths that are ahead. And in this case, there are 3 toll booths. However, I don't have to go through all 3. I have options. So I'm almost like it splits into 3 lanes for me, and I get to pick my lane. And so it actually makes it a little easier to pass through that circuit. And you'll see what happens to the current as a result. But what I want to do is show you how we derive this equivalent resistance equation. So I want to basically replace R1, 2, and 3 with one resistor that would be equivalently fast or slow through there. All right, and so that's always going to be equal to the supply voltage over the total current. But we don't know the total current. All right? However, we would get that total current by just adding up the individual currents through each resistor, right? Oops, sorry, it should be I3. I'm just deriving this, right? But if this water was splitting along 3 pathways and then merging back together, right, it would make sense that the currents through each of those 3 would just add up to that total. And Ohm's law says that each of those currents would be equal to their voltage over their resistance, V2 over R2, V3 over R3. So if I were to add the currents, that's really another way to show that. However, we also know that each loop back to our source, here's one loop, here's another option, and here's a third loop. Every individual loop will always drop the supply voltage, which means that V1 must be equal to V2, which is equal to V3, which is equal to whatever the supply is. Every loop sees all of that supply voltage, and we saw that in our mini lab. So we can actually take this equation, and instead of having V1, V2, and V3, you have something like this: V supply over R1 plus V supply over R2 plus V supply over R3. And we can simplify that because I have all those V supplies into one equation that looks like this. It's a little bit confusing, especially when you have it in fraction form, but it looks like this. 1 over R1 plus 1 over R2 plus 1 over R3. And this is true for any circuit in parallel. And you can have as many resistors as you want. So this is our equation to find equivalent resistance in parallel. And you need to know that. Now, there's a nice feature in your calculator. 1 over a value is just taking the inverse, correct? Or taking it to the -1 power. So another way to write this equation would be to write it with inverses. So I can write this as R1 to the -1 plus R2 to the -1 plus R3 to the -1, and I can raise that whole thing to the -1 to put it in the denominator. So when we do it in our calculator, that might be that might be a better way to think about this, so we don't get caught dealing with all these fractions. All right. So let's continue looking at this now. So we now know how to find equivalent resistance, but there's a couple other things we know. So we know that each voltage is equal to the supply voltage, and we also know that the current is going to be split up when you have these pathways. So it turns out I1 plus I2 plus I3 is going to be equal to that total current. All right, and that's always going to be true when you have parallel splits. So let me define those last couple comments here. So again, current is going to be not constant now, whereas it was constant in series, but now current is the one that is split or shared. Current is split or shared. And again, it's going to depend on how long it takes to get through those toll booths. More cars will be able to get through, right? So it's shared proportionally to the amount of resistance. More resistance means less flow will go through that pathway, right? More cars will go through that easy pass lane than through that gated lane, right? And voltage is going to be dropped equally in each pathway. If your circuit is only in parallel, those pathways will all drop the supply voltage. Now, we did see in our mini lab when you had a resistor on the front end before the split, you drop some voltage there, and then each pathway drops the remainder, right? We saw it drop 6 volts and then 3 and 3. Each pathway split it equally, though. All right, so these are some rules that define parallel circuits, and we're going to solve some problems here and start looking at how we do equivalent resistance, and then we can start looking at ones where you get combination circuits. But you have to know these rules. You have to be able to identify what's in parallel, what's in series, and apply some of these basic rules to the circuits. And if you can do that, then breaking them down becomes a little more of a simple task.